Welcome! I'm Simon and I will walk you through quantum chip design. Structure of this video is theory. First, there will be introduction to quantum, then quantum hardware part, then quantum hardware fabrication. In design, we will take a look at introduction, calculation of values, then circuit simulation, then layout using Qiskit model, then post layout FEM simulation, and then we will do GDSI inspection, render, and summary. There are many types of quantum computing, including trapped ion, which is quite popular. There are two major companies like IonQ and Quantinum, and bunch of smaller startups. Another very popular type is neutral atom. There is a lot of companies across US and Europe, um, and a lot of startups. They have quite a decent valuation. The major companies in neutral atom, and the technique is quite advanced, and they have really nice decoherence time. Major superconducting tech is very popular, and there are very big players like IBM, Google, and a lot of many corporates. There is a lot of startups which have very decent valuation like IQM or Jetty, and a lot of smaller startups. So superconducting is a leading technology, and there is a lot of development, and it's very, very popular. Here is our quantum computer architecture. It starts with control electronics, which is basically FPGA and analog circuitry around it, including some RF parts, which is room temperature, and it is meant to control cryo stuff. Um, you can think of companies like Zurich Instruments or quantum machines or Qblocks. A lot of companies are in this field. Then there is hemp, which might be room temperature. Below room temperature RF amplifier, there is a cryo amplifier, which is RFIC. It is at 800 millikelvin, I think. Um, then below cryo RFIC, there is a traveling wave parametric amplifier, um, which is at 100 millikelvin. This is used to amplify RF signals. Then below this stage, there is finally QPU stage, where our quantum processor sits. Mm, it's around 10 millikelvin. So here's our Josephson junction. Basically, it is two metal parts. Metal part is aluminum, which is superconducting at certain temperatures. And there is a small insulating barrier, which is aluminum dioxide. Mm, there is also squid, which is basically to Josephson junction in parallel. This is the picture on the right side. Here is our Josephson junction under microscope. Mm, there is a theory of superconductivity, which is connected to Josephson junction and superconductors in general. There is perfect DC conductance, very large inductance, like very small Josephson junction, uh, can have like 20 nanohenries, which is very, very large, or mm, and also ability to expel magnetic field. Here's atom and its energy. You can see atom visualization um, on the left side. In the middle, there is atom and its electrons, and we can basically control the energy and energy transition of our transmon using electrons. So if we add some electrons, we can push our transmon to higher state, we can excite it to higher state, and this is the picture on the right side, where we control our transmons using adding electrons. Here's our lumped elements representation of qubit. You can see a gate capacitance in the middle, and LQ is our Josephson junction, and there is capacitor in parallel because we are talking about transmon qubit, which is a charge-based qubit, so there is always capacitor in parallel. There is also resonator, which is represented by inductor and capacitor in parallel. We can see it here. So this is our resonator, and you can see visualization of such system. There is a coplanar waveguide or transmission line, which is basically our resonator. This is the simple line, and here we can see our qubit, which is just Josephson junction. So this is our lumped elements representation of qubit. There is energy spectrum for each transmon, which is basically a ratio of energy of junction and energy of capacitor. It tells us transition frequency of each qubit, and we can refer to this paper where we can see more details about transition frequencies. You can see there are different spacings for each qubit type. Here is a comparison of classical oscillator and nonlinear oscillator. You can see there is a big difference between wave function. The first has wave functions such we would need infinite energy to reach another excited states. If we can take a look here. For our nonlinear oscillator, we have cosine function, which basically tells us that we can reach next kind of state very easily. So this is the major difference. So here's our first type of qubit. This is a transmon qubit. We can see picture of IBM quantum chip using 7 qubits. This is transmon pocket, and this is cross pocket. It is charge qubit and quite old, I'd say, but pretty relevant today. Here's our fluxonium qubit. Fluxonium qubit is different because it is operated by flux rather than charge. It has higher decoherence time, it is less noisy, and it is a newer type of qubit and very popular in quantum computing. I think it was developed at MIT. There's also cat qubit, which is special in the way that it has bit and phase protection. Um, um, Also, the state is encoded in photonic states. It has higher decoherence time, but the circuitry is a little bit more complex, I'd say. So let's take a look at parts of quantum computers. This is a very important part. It's called air bridges, and it is here to connect different islands. If we have some coplanar waveguide and need to connect it, and there is no way to route it in our circuit, we can basically use this air bridge to connect two different islands, and it is kind of very nice way to get over this problem. Also, there is coplanar waveguide, which is a very basic thing for a quantum computer. This is the thing here. This is coplanar waveguide. We have basically one line with defined width and gaps, and we need to calculate its target impedance for 50 ohms preferably. We can do this by putting width parameters and gap parameters, and also substrate um, thickness and um, permittivity um, or substrate, which is typically silicon, right? So thus we can calculate 50 ohm impedance. There is a representation for resonators or meanders. You can see this inductor and capacitor, and this basically are coplanar waveguide or trace, and here is lump representation for it. We can kind of measure 50 ohm impedance using VNAs, vector network analyzers, and yeah. Next thing we have here is a term called gate fidelity, which is our design goal. Our we aim for gate fidelity as high as possible, because this is what tells us how accurate is our quantum computer. So we aim for 99.999% gate fidelity if possible. Quantum error correction. This is next goal, to have fully error corrected quantum computer. This is basically technique that protects from unwanted behavior like phase flip error or bit flip error. So we don't want any errors in our quantum computer. Scalability is next term. Uh, we want to have mm, like as many qubits as possible, and we want to fit it on very small space, and we also need to take care of connections, and this is basically quantum computer with a lot of qubits. So you have a lot of wires here. As we scale our system up, we add more qubits, we will have more disconnections. So this is another goal to, so we can scale our quantum computer very well. This is our quantum chip workflow. We start with concept, so we need to define which type of qubit we will use, number of qubits, some preferred frequencies, and things like this. Then we move to lumped elements, where we simulate our frequencies, and then we can move to layout, where we actually do our quantum chip, connecting our qubits to resonators, flux bias, microwave drive ports, and similar. Then we need to do a post layout FEM simulation, where we verify our design. And next step is preparation for fabrication, or GDS, generation and inspection of these files. So this is our quantum chip workflow. Next, we have our layout and description. So we will take a look at 7-qubit quantum chip with a central flux tunable qubit, inspired by paper from IBM. You can see it's quite simple design indeed. So let's break down our layout. We have pins or ports, which are very important for connecting our quantum chip to outer world. We can do this by wire bonding, where we add very thin gold wire, and thus we can connect our quantum chip. Next, we have central flux tunable qubit, which is here. We have normal connections to other qubits, but one additional flux tunable pin port. Then we have coupling bus. We just simply connect our qubits by this. Then we have readout resonator or readout bus, which is just connection to our qubit, and we can simply read out our qubit by this. And then we have normal qubits here, which are just 2-port devices. Here is our flux pin for central qubit. There are many types of processors. Most common type is transmon, and there are a lot of revisions or variations of transmon qubit. There is, let's say, interdigitated transmon, which is oldest one and quite simple one. Then we have cross transmon, which was developed by Santa Barbara, I think, and Google use it very often. There is transmon pocket. There is some advantage for each qubit actually, but those are minor things like higher decoherence time, or more connection pins. Yeah, so that's for transmon. Then we have other types of processors and qubits. Starmon is very nice one because We have more ports. We have four coupling buses usually, flux bias line, microwave drive line, and readout line. So this is preferred for more complex devices where we need more ports and more connections. So this is very good for designs that are very complex. We have cat qubits, which are very different in nature because of the way they encode their qubits. So they have different advantage over Starmon. And there is also fluxonium, which is kind of which has more protection about unwanted behavior from other world. So it is also operated by Flux. So also very interesting qubit. I think it's newer one compared to Transmont. It is definitely more advantages to it. So more advantages. Um, here's our qubit characterization. First, we start with lambda elements, where we basically break down our qubit and we simply define our Josephson junction, capacitors, gate capacitances, and connections um, to the qubits. Then we need to do some simulations. So for simulation, we can do scattering matrices, which is basically S parameters, impedance profiles, and other circuit simulation parameters. We can also do some Josephson junction characterization, like some current simulation of Josephson junction. Next, we have FEM simulation. We are talking about EPR, which is a technique to evaluate quality of quantum chips or Josephson junction. Mm, Here's basically the workflow for this technique. We need to use some FEM simulator, which is compatible with EPR. Um, um, it uses very big inductor model of Josephson junction for FEM simulation, and um, there's more detailed description of its process in the paper, so you can take a look. For FEM simulation tools, we can use either ANSYS, which is paid and very powerful, or Elmer, which is free, lightweight. We don't have support for so many add-ons. So less popular. Then we have AVS Plus, which is cloud-based, very good. You have some support for Python interface and I think EPR as well. You can do a simulation of electric fields and S parameters as well. Next we have FEM simulation types, which is um, basically what we can do with our FEM simulation software. We can do scattering matrices like impedance profiles, S parameters, S parameter of resonator or a qubit. So like simpler tasks. Then we can do eigenmode, EPR, electric field simulation, which is good for evaluating our quality of qubit, which is very powerful. And then we can do capacitance. extraction, which is very good for now finding kind of mm, capacitances of our qubit, um, like um, a very powerful thing, or we can also use it for capacitance of our substrate. Mm, so very useful for quantum chips and traveling wave parametric amplifiers, where we have more complex shapes integrated into our chip. So very useful. Then we have fabrication materials. We have top metal, bottom metal, insulating layer, and substrate. For substrate, we usually use silicon or sapphire. For metal, we use aluminum, tantalum, niobium, and for insulating barrier, we typically use aluminum oxide. So this is our model of Josephson junction. Here we have fabrication process, which starts with preparation, then spin coating. We spin coat it at 9,000 RPM to have very uniform coating, and we apply photoresist layer. Next, we do exposure to um, just some type of lithography machine. Not sure about specific AUV or UV might be fine for this. Not sure. Um, Next we have development on chemical solution. Next is etching, which is most likely some reactive ion etching or inductively or ICP, inductively coupled plasma, I think it's the name for this. Next we have metal fill, which is some sputtering process, and this is our metal interconnections. Next, we have fabrication foundries, which is global foundries for higher quantities or skywire. Can also manufacture Josephson junction. Or we can go with university fabs or labs, which might be very good for low volume prototyping of our quantum chips. So it's up to you what you will need. Next, now we will have our tasks. So I picked this quantum chip from IBM. It's an qubit type, and we will follow this paper, and we will try to design it. So there's also a link to theory for quantum chip, so you can follow this one as well. Let's take a look at the paper from IBM. We take inspiration from this paper. It's called Hardware Efficient Variational Quantum Eigensolver for Small Molecules and Quantum Magnets. Here we can see our layout of quantum chip. There is also some description about algorithm. We can scroll down there to see layout. There is layout with connections to the quantum computer. There is also some description about our hardware of quantum chip. It tells us more about nature of our quantum chip. As you can see, there is, for the experiments discussed in this paper, we use 6 of these qubits, including the central flux tunable qubit. There is also a little information about resonators and also about fabrication of quantum chips, type of process used to actually fabricate this quantum chip, and materials used for this process. It uses aluminum-based juice injection. Here you can see frequencies of our qubit. Here is frequency of a first qubit. We can take a look at the simulation I made previously, and we can see from the LOM that the frequency of our qubit is around 5 gigahertz, and from the paper it's quite similar. There is minor difference. The coherence time um, is also very similar. There is also frequency of resonator, and that's all we basically care about. Now let's take a look at the softwares we will use. We will need AVR, which you can have free trial. We will use this for lumped elements. Then we move to Jupyter Notebook. It's environment for Qiskit metal. Then we will need some FEM simulator. You can also have free trial or student license. Then we will need FreeCAD to export 3D files, and we will need Blender for visualization. Let's do lump simulation. For this we will use AVR. We need to create new schematic. Once we have this done, we need to take a look at the paper to know how to actually create lumped elements schematic. It's from the paper called Circuit Quantum Electrodynamics. We can scroll down to see. This is a representation for resonator. Here we can see a representation for transmon qubit. It uses Josephson junction and shunt capacitor. Here is our connection of transmon with resonator. You can see that the blue one is resonator and the green one is transmon. And we will need this one to replicate, or alternatively the picture above. Here. So for this we will first need to calculate resonant frequencies of a transmon and coupling bus or resonator. We will use online calculator for this. We need to pass capacitance, which is about usually 50 femtofarads. then we need to pass inductance. You can see that resonant frequency for our qubit should be about 5 gigahertz. So we can add these values to AVR. For resonators, we typically have inductance of 15 nanohenry. So our schematic should look like this. We need to pick resonator, and we also need to pick capacitor. We need to change values, so we will do project options, global units, edit units. We'll choose femtofarads, nanohenries, and gigahertz. For this, we will have 50 we will say 45 femtofarads and 15 nanohenry, and this is a small capacitor, and we will choose a value of 5 femtofarads. You also need to add ground. This is our for qubit, we should use Josephson junction, but since we only need S parameters and impedance profile, we can also use just inductor, because FEM simulator uses also just large inductor instead of Josephson junction to compute electric fields and EPR. So for this, we can use just inductor. If we need more advanced simulation, such as simulating currents and other parameters, we should use Microwave Studio with built-in Josephson junction model. You need to change this to 20 nanohenries. Now we need to add what's called graphs, new graph, rectangular, measurement, dB, all sources as parameters, and we also need to add measurement for port 2, which is our qubit. We will also want a graph for impedance profile, so we can scroll down and select Z. We will have impedance profile only for resonator. Now we need to change project options. Frequencies, we will start at frequency of 1 gigahertz and stop at a frequency of 10 gigahertz, and we will have a step of 0.001. Now we have our graph of impedance profile, then we have our graph of S parameters. Here is S parameter for qubit, and here is S parameter for resonator. We can change labels by changing this value. This is a resonator, this is qubit. We can now close this and move to the layout. For this, we will need to use Qiskit metal. So we jump to the Python, and here you can see our file. We start with importing important libraries. Here is our build library for image import. Here is our Qiskit metal definition, and here is our PyAPR. So we run this command. Now we define our design here. Here we start our GUI, and there is a definition of chip plane of itself. This is the ground plane of a chip. There is a size of a chip, and there is offset from center. We usually define this in the last step where we know how big our design is depending on our components. Now, before we start designing, we will need to add our transmon. For this, we will use transmon pocket 6. So we will go into the libraries, qubits, and transmon pocket 6. We create one, and now we need to modify it. To do this, we can modify this in a Python script because we need to add our pins. You can see there is no connection paths available. There is just connection path A. We need connection path B as well. So we save our design. We click save, and we save it. Now we have our Python script saved. We can open it using Notepad, and all we need to do is copy this command with import of transmon pocket 6 and paste it into our Python script. I've already have this transmon here. All we need to do is copy this A pin parameters and options, paste it and rename it to B and change some parameters. So we run this step to see this. Now we have our transmons defined. Let's take a look at our first transmon. You can see that now we have our connection paths A and B. In order to change a position of our pins, we need to adjust these two values. You can see a location width and a location height. We can do this by changing this to either +1 or -1 or 0. We can see -1 is down here, +1 is up there, 0 is at the center. And we can do the same thing with the other option. So this is on the other side. This is on our correct side. We can also change path pad width and pad height. So let's change this value to see. You can see the pad is now bigger. We don't need to adjust any other values, so we can all leave it as it is. For the central flux tunable transmon, all we need to do is to choose transmon pocket with charge line and do the same thing with our pin definition. We need to add another pin B in a script. So let's take a look for other components we have there. The other component is called line T, which is very simple. All we need to define here is orientation, position, X, which is horizontal position, and position Y, which is vertical position. You can see our line T here. So there is not a lot to define here. We can move to another component which is called launchpad warm bond. There is also very little to define. There is only orientation, position X and position Y. So we execute this step. We can see our launch pads are here. We have 7 launch pads. We need to delete this transmon, which was just for example. We have 7 launch pads. We can take a look. The upper ones are at the position of 4,000 micrometers, and the lower ones are at minus 2,000 micrometers, and with orientation 90 degrees. We can jump to other step, which is route mixed. In this step, we need to define few things. I'll execute this step and show you a split screen so you can see it properly. We have our route mixed number 1 here. We need to define few things, which is start pin. In our case, it is LT1. So we click at LT1 and see for this pin we will use second end. So we need to write down here second end. And for end pin, we will use component LT4, which is this one. And we will use second end as well. So we will write down second end here as well. The other parameter we have here is lead, which basically tells us the start state of meander from the beginning. So in our case, it's 200 micrometers from the beginning, so it forces the meander to be straight to this place. Next parameter is anchors. For this, we defined the points which forces are route mixed to route our meander. In this case, it's the first point is 0.5 and 0, which is here. The other point is 1.83 and 0, which is this one, and the last one is 1.83 and 1, which is this one. So we have 3 points, and now we need to define a style of our road. So we can see from the point 0 to our first point, so it's from the beginning to the first point. We force it to be S, which is straight, so the meander is straight. Then from the first point to the second point, which is here, we force it to be M, which is a meander, so we can see it's meandered here. And from the second point to third point, we force it to be straight as well, and then from this point to the end, we force it to be straight as well. So that's for the anchors. Now for the fillet, I can actually show it to you more visually. Fillet tells basically how the software should round the edges of the meander. So if we change the value to 150, you can see the edges are not rounded anymore. If we do 120, maybe 100, or maybe 70, you can see the edges are a little bit more round. If we say we want 90, the edges are nicely rounded. Then the other value is total length, which tells us the length of the meander or the whole road. We can force it to be 14, so you can see the meander is very big. Next, there is meander options, which basically tells us how the meander should behave. There is spacing values, which tells us the spacing of the meander. If we change this value and lower this to, let's say, 140, you can see the meander is more dense, but it also affects the fillet value. So if we say we want 220, the meander is quite big. It's not that dense, so you can see there is also another value which is called asymmetry, which shifts our meander to the one side or the other if we add minus sign. And this is all we care about in meanders. For the other meanders, the process is quite similar. All we need to do is set up pins, anchors, total length, meander, spacing, and asymmetry, and we should be fine. So we can execute this command, and we have other meanders. Next step, we need to route this line T with our qubit. For this, we will use route straight. We have two parameters, which is start pin and end pin. for start pin, it is our component LT1, um, which is this one, and we have our you can see we have our prime start, and we can connect it with qubit on. Um, we can connect it with qubit 4 and pin A. This is basically it. It's very simple for road straight. So we can execute this command. Now we can add our logo. We need to choose correct naming for our logo. We need to have it in our repo here next to the our Python file. We need to copy name and paste it here. We can set location by adjusting offset value, and we can adjust scale. Here we can draw each rectangle, so it's not just a metal layer, but also nice edged frame. The same is for our icon. We can have our logo and icon as well. So we can execute this and wait a few moments. Now we have our logo and icon rendered. We can move to Fem Simulator. We can open a new project. New project, new HFSS file, and we will render HFSS simulation. You can see it is rendering. We need to wait a little while. Now we will simulate our resonator. we need to assign ports. So we do this by assigning excitation port, lump port, add integration line, new line. And we need to do the same thing on the other end. Let me oh, I just open this one, add setup, add frequency sweep. We will need frequency from 1 gigahertz to 10 gigahertz, and we will have 4000 points. We need to add results, create a rectangular plot, S11 parameters, dB, and sweep. We need to do the same thing for impedance profile. Now we click Analyze All. Let's see, there are some messages. Non-manifold vertices. So all we need to do is to delete this one and run Analyze All again. We can clear messages. Once we have our simulation done, we can take a look at our plots. It looks quite okay. And we can do simulation of capacitances. We will need to export this project into Q3D. Now we'll click assign boundary rate in conductor, perfect electric conductor, about 200 nanometers. Now we define our nets. Now we click analysis, add solution setup. DC and AC, we will unselect this. We only need capacitance. We will click OK. We will click on results, create matrix lab report, rectangular plot. Now we choose adaptive bias, bias, C matrix, absolute, and we choose pad gate, gate ground, pad 1 ground, uh, pad 1, pad 2, and that is all we need. Now we click simulate, analyze all. Once our simulation is done, we can take a look. And now we can see capacitance from pad 1 to ground around 50 femtofarads, which is our capacitance we simulated in lumped element simulation stage in microwave office. We have other plots, which is pad to pad, which is around 30 femtofarads, and the other ones are below 10 femtofarads. Now we will move to simulation of only one qubit for EPR and electric field simulation, because simulation of the whole system would be very computationally heavy, so we will simulate only one qubit. So let's get started. To execute first few commands, here's our definition of EPR. Here we start HFSS. Here we activate design. Here we render our design. Here we choose properties for our qubit. And we click analyze. It will take a while. Now we will need to plot our fields. In this step, you can see plot of our fields. Here's mode number 1. Here's our Josephson junction. We'll clear fields and set mode 2. Here's mode 2. Now we will run EPR. We'll set up. Here we choose our name of Josephson junction, rectangle and line. We can find the name here in Fem Simulator. And we will click run EPR. You can see some values from EPR. We care about this value, which is EPR of substrate. And you can see there are two modes. Mode number 0, which is at around 6 GHz, and mode 1, which is cavity mode, which is 48 GHz. Now we will jump into LOM analysis. Here we render our qubit into Q3D. We need to specify a name for qubit, which is Q4 in our case, and we need to select pins properly, which is A, B, and charge line in our case. We set up our sim. We run our transmon pocket. we need to choose correct name for this, which we can see in our um, in our code here. Here, transform pocket. So this is our name. We can take a look at the outputs from the LOM simulation. You can see there is our frequency of qubit, energy of capacitor, and energy of junction. Inductance of our qubit, and the coherence time. You can see there are values for capacitance from Q3D simulator, which we simulated manually. Now you can see some values here. Now we have values we care about. And we can pass them into SC qubits. All we need to do is copy these parameters and paste them here. Just be careful, this is in megahertz, so it's like this. Here's our wave function of transmon. We can take a look at energy spectrum, and we can also take a look at the coherence time, which is here. We can select effective T2 and scan over EJ, so we can see our decoherence plot here. Once we have this done, we can generate GDS files. We will generate GDS files from this layout. We'll select location. We'll call it my design. We select fabricate true, and that's it, and we can click export. we can view our GDS files in ABR. We just need to open this, and here's our GDS files for fabrication. Now we will export our quantum chip into Blender and create preview. So we will click modeler, export, export as a step file, and we will call it chip. We will save it, and now we can open our quantum chip using FreeCAD a step file and export it into Blender format. Now we will select all the shells and click export as object file. We will call it chip as well. We can close this. We can open Blender. I already have Blender tutorial, pre-made example. This is our scene. It uses plane, light, and camera, and this is our quantum chip, which it's already done, but I'll show you how to do it from scratch. So we will delete all the shells. We will import, or we can just drag and drop it. Here's our quantum chip. We will move it horizontally, scale it down a bit, rotate using R. By clicking X, we can rotate it. We will click 90 degrees, minus 90 degrees. We will move it upwards by clicking G and Z, and we will move it closer to the camera using G and X and Y. Now we have our quantum chip. All we need to do is to select our plane, click Shift D, G, and Z. Now we will click Tab. We will select all the edges. We will click Shift D to duplicate, G and Z to move it. We'll move it by 5. We will click wireframe, delete all the geometry here. Now we will delete. Now we will click let me is there any here's our geometry. We'll select it and delete it, all the vertices. We'll need to go to wireframe, delete all the vertices. Let's do it again just to be sure. Now we will select our frame, click F, and now we will drag it down by clicking G, Z, and -5. We'll scale it down a bit. We'll click 7 to see. Now we will scale it. Extrude it by clicking E. We will extrude it by 0.07 in the direction. We will go upwards with our second plane, and we will extrude it as well. And we will assign materials. For this, I already pre-made some materials. To see materials, we need to go to the materials tab here. We can click material 001, and for this we will choose color 1, and here's our quantum chip. We will go to camera, render image, and here's our quantum chip. So that's all for quantum chip design, and hopefully you enjoyed this tutorial.